So yesterday we closed with a particular problem in the previous binary search session that we had. There was n numbers and there was an array of n bits that was zeros and ones. Okay, something like this. And you had a possibility of converting at most k bits. You can flip at most k bits in this array, and you wanted to find out the longest possible subarray that contains all ones. So do you remember this particular problem? That given an array, find out the longest subarray that you can create, which contains all one, such that you can change at most k number of bits from 0 to 1 or 1 to 0, whichever way you want. Okay. So in this particular problem, we discussed the solution for this using a binary search. That okay, let's say we binary search on the answer. So binary search on the answer. So this is a particular technique that we discussed in the previous session, that for most of the problems where you have to find out the longest, shortest, or some sort of problem like this, you generally try to use binary search on the answer, such that once you know the answer, since it's the minimum or maximum, it will be a monotonous space, and based on that you will be able to find out the you will need to design the check accordingly, right? So for this we talked about a binary search solution where we searched on the length of the segment, and let's suppose we want to check for a length segment of x. Okay, so what we did is we went through this whole array on every window of size x and checked, can we convert at least one such subarray of size x into all ones, right? So the only condition that lies over here is, if you're checking some particular window of length x, the number of zeros in that particular segment should be less than equal to k, right? If this is true, then you can convert that particular segment into all ones, right? So binary search on the answer, and for particular x length, you want to check whether there exists a x length subarray or not in the array. So you just check out each of the windows, and for doing this, what we did is we maintained a window kind of thing where you kept the count of number of zeros, and you remove last element and add a new element after that into the set. So you just need to maintain this property, right? So is this question, like, is this binary search solution clear to everyone? I think we discussed about this in the last session. So now today we'll be starting with binary search again, but with a different logic. Okay. So binary search can be applied to this particular problem in another logic as well. So we will discuss that. So in yesterday's session, we discussed binary search on answer. So now we will look at one more particular type, which is binary search on every L. Okay. Okay. So let's suppose we consider a particular L at a point. Okay. Let's say we say that this is our L. Okay. Now we want to find out the longest subarray that starts at L and ends at some R, okay, such that it has less than equal to k number of zeros. Make sense? So if for a particular L, we want to find out the farthest R, right? So that this range is as large as possible, because we want to maximize the length of the subarray which contains ones, right? So we want to find out from this L included, what is the farthest R, such that the number of zeros in that range is less than equal to k, right? Now, if you notice, for this particular L, this R is also binary searchable. Is this part clear? Why? Because if this is the L, then the number of zeros can only increase in this direction, right? So when you see the first zero, let's say it's yes, okay, and then let's say after 2 zeros, now you cannot take any more zeros, so it's still yes, but when you see the third zero, it's no. When you see the next any element after that, it's all no, because you cannot make your R up to these elements. Why? Because if you make your R up to this, the number of zeros taken in your subarray would be more than k, right? Let's suppose k is equal to 2, so you can start from this and take up to just 2 elements, not the third zero, right? So for every L, the range of R that we're talking about, such that the number of zeros is less than equal to k, is also a monotone space. Is this clear to everyone or not? Can I have a +1 on the chat if this is clear? So now, if this is understood, then we are done with the second approach, that we want to find for every L, let's say for every L, if we can find out what is the farthest R, and if we do this particular thing for all L's and take the max out of all, won't we get the answer? Like, let's say there is this array, okay, and there is this optimal range. There is some optimal answer, right, for this particular problem. So let's suppose that is from L dash to R dash. Okay. So since we are taking this particular approach that, okay, for every L in the array, like for every starting point, this, for every starting point, we will find out the farthest R that is possible. So when we will consider this particular L dash, we will definitely find this R dash. So this will get considered. So across all the different L's possible, if we take the maximum length subarray that can be created from that L, then out of those max, we will get the one with the longest range, right? Is this part clear to everyone? Now, there is one part left in this. When you're starting with L and you like start with this element taken and you want to check whether can you take up to this element or not. How do you do this check efficiently? Prefix sum, right? Okay, let me explain this part. So for this particular L, we will try to find out the farthest R that is like such that the number of zeros is less than equal to 2, right, from L to R. So it is nothing but like prefix of R minus prefix of L minus 1 is greater than equal to, is less than equal to K, right? And we know the index L, so L is fixed, so we can shift this to right hand side. So we say that, okay, this is prefix of R is less than equal to K plus prefix of L minus 1, right? Now, since right hand side is fixed, we just need to find the farthest R which follows this property. And we know that in prefix sum, since it's zeros and ones, and this prefix sum is built on zeros, like prefix sum, this will give us the number of zeros in the range L to R, okay? So we can obviously build a separate prefix sum along with this, right? That to find the number of zeros in the range L to R. And with that in place, we can just quickly check whether what is the farthest R that will work with this. Okay. And that R will be the like endpoint, and from that we can take the subarray size and take maximum across all the L's. Okay. Is this part clear? How are we doing this? So this prefix of R, prefix sum of zeros and one array is always a increasing array, right? So that is a binary searchable part. So we can binary search for the largest R in this prefix array. Make sense, everyone? Is this part clear? Can we let's then quickly code this particular solution so that this all makes sense, because this is a new idea that where for every L we binary search, and to help our binary search we keep a separate prefix sum. Okay, so let's look into how we can code this particular solution. Fine, so let's look into how we can do this. So what we will need is, we will first of all have to define the n and k. So we will have to define particular L. And the vector of integer ARR, right? These are the two, these are the only inputs that we have in this particular problem. Right. Now with this in place, we have our input. Now we want to particularly solve this using the prefix sum idea that we talked about just now, right? Yep. So now we will also keep a vector of prefix sum. and let's build the prefix sum over here itself. So let's prefix dot resize n, okay, and prefix of I is equal to arr of I, and if I, then prefix of I plus equals to prefix of I minus 1. Makes sense? So I'm for now assuming that everything fits in integer. If it does not, you can take it long. Just let's just quickly assume that okay, it works in integer. So by now I think you should have should have built some caution about these things, that whether my value is overflowing or not. If you're not sure about, you will be able to handle this every time in problems, take everything in long. Okay, but like ideally you should do it in like keep it in the variable that is like just so that it just does not overflow. That's it, the smallest such size. But even if you're not sure that you are able to handle that in every problem, just take everything in NL, like that should work. Okay, now we will have answer. So we build the prefix sum. So answer is the longest subarray range that we want to find, and now we just need to do for I equal to 0, I is less than n, I plus plus. Okay, and integer temp, if we try to find the r, so we will use this particular expression, so we want to find the r such that it is less than equal to this. So there is this less than equal to, right? So what do we use over here? How do we find the last index where it's something is less than equal to? Yep, that's upper bound minus 1, 2. So in this particular problem, what we will do is we can also, we don't just need the r, we just need this r minus l, right? So we will quickly calculate the size itself. So we know that in a subarray, if upper bound minus begin gives us the number of like the total number of elements less than equal to some particular value, right? So we will directly use that. So we will start with the index I. So make sure you write this or else it might get wrong. So prefix sum of I, and this get prefix sum of n from I. So from the index I to n, we want to search the particular value of uh, this particular value, right? K plus prefix of L minus 1. Now we need to be careful when this L minus 1 becomes 0. This L is nothing but I over here. So we will write this something like this. If I is greater than 0, then take prefix of I minus 1, or else take 0. Okay, so we will just write this shorthand notation for this particular part. Okay, so if I is greater than 0, take prefix of I minus 1, or else take 0. So this is the upper bound part minus the first element, that would be prefix dot begin minus I. Like we have the first element as this, right? Prefix of begin plus I. So that's where we are searching from. So we just subtract that particular element, and this gives us in the part I to end what is the number of element that is less than equal to it. So if we close this properly, yeah, we have not written upper bound, right? Make sense? And then this is the length. So we just have to answer, we have to just update the answer equal to max of answer comma temp. Is this part clear? And then we just see out the answer. That's it. Is this whole idea clear? Anyone having any doubt on this one? So at times you will need to binary search on every L, and to calculate the property very fast. So we had to find out the number of zeros in the range L to R, right? That's what we wanted to calculate. And to keep it fast, we used prefix stores ones, not zeros. That's correct. So we will make this 1 minus this. Okay. So we had to build prefix sums on zeros, right? So this will keep. So we will make prefix of I equal to 1 if it's 0, or else if it's 0 then it's 1. So you can use minus, you can use XOR, anyone, like it flips the bit basically, and then we build the prefix sum, right? Now I think let me quickly check. Okay, yeah, that's correct. So is this part clear to everyone? How we are doing this part, like how we are using this upper bound and things. So if this code is clear, can I have a +1 on the chat? Then we can move to the next part. Okay. Hope you get the idea of things. So this is the main building block for the 2 pointers. Now let's move into how we try to optimize this particular approach. So for this particular problem, we will note a particular property. Okay. So we had a lot of zeros and ones, something like this, right? Something like this. So for a particular L, we found out that the optimal R up to which you can go is, let's say, this. Okay. Now let's say you try this next L dash. Now by the setting of this problem, R dash can only be from this to this particular part. It cannot be less than this previous R. Why? Because let's say you took this L to R. Now this had less than equal to k zeros, right? Now of course this L dash to this R would contain less than equal to k zeros. Makes sense, everyone, right? That if L to R is less than equal to k zeros, then if you just remove one element, then it still will be less than equal to k zeros, right? So this will still be holding the property true that for L dash, at least from L dash to R, it's valid. And then we can push R more towards the right if we want to, right? That's a possibility, but it might happen or not based on whether we have zero next or something like that, whether we have removed a zero or we have zero next and so on things, right? So that can change, but the property is that if the L and R were something like this, then for the next L, for any next L, the R will be, if L dash is greater than L, then R dash should be greater than equal to R. This property holds in this particular problem. Is this clear to everyone or not? Can I have a +1 on the chat? Because this is the whole gist. Okay. So once you have this particular property holding in a problem, you know that you can apply 2 pointers to that problem. Okay. So this is the only property that you need to check, to check that, okay, a problem that you can solve in binary search, can you reduce the complexity using 2 pointers or not? This is something which will give you the check. Okay, that is my right pointer also increasing if I increase my left pointer. Okay, that's the only check. Make sense, everyone? So now if this property holds, then what we can do is, in this particular problem, what we were doing is we maintained a window, right, of what is the length that. Okay, let me start from this only. So we maintained a window, right? Something like this. Okay. So let's say we started a window something from over here to over here. Okay. And we say that for this L, you can only go up to this R because let's say k is equal to 1. Okay. Now, as soon as you make this particular L move to the next element, okay, L over to this element, let's change this element. Okay. Now one of the 0 decreases, right? So you can now push the R to the right as much as you can, unless you fail this particular threshold given in the problem. So you can push the R up to this particular point, right? Now for this L, again, this R would be the maximum possible R, and you can take the maximum again, like we are taking a running maximum, right? Like we have an answer variable which contains 0, and we are continuously taking max for every possible L, right? So we are doing the same thing that we did in the binary search. It's just that for every L, we are not doing a binary search. Rather, incrementally, we are increasing this R pointer towards the right. Okay. So for this L, we got this R. Then for this particular L, the R remains the same because still we have not removed this 0, so we cannot take a new 0. For this as well, it's same. Now when we come to this particular point, we see that, okay, now we can remove this particular, we remove this 0. So now my R can increase beyond this, so it can go up to this. So if you note, from this it was up to this, so either R remains the same or it moves towards the right. This is holding true, right? That from this L it is moving to this particular right. So both my pointers L and R are always moving towards right. Make sense? So in total, the total traversal that I'm doing on the whole array is order n. Okay, and with this traversal, I will try to push the R as much to the right as possible, so that my subarray is of maximum size, so that I don't violate the condition number of zeros is less than equal to k. Okay, so that's the whole strategy of 2 pointers for every different problem, that you have a L and R pointer and you will try to push them. Okay, now before we implement, we will quickly rename 2-3 things. So this is just my particular idea that I use when I'm thinking about a problem. So what I do is I particularly take this, like there are two parts, right? Head and tail. I call them head and tail pointer. Okay. So you can think of it like a snake that is eating one by one elements. Okay. So next element, it will try to eat a new element as long as it can. But let's say this is the property by which it's like stomach is full, then it cannot eat one more element. So now he will remove one and then try next one. Okay, that's the whole part. So we will maintain this R pointer with a head, like a name head, and this one as tail. Okay. Now at some point of time, there might be a possibility that you cannot take even one element. Why is that? Let's take this scenario that k is equal to 0 and the array is 101. Okay, just 101. So for this L, R is equal to the same value, right? For this particular tail, head will be equal to over here only, right? The tail and head will be both here. Now when tail is over here, like this is your left endpoint, you cannot even take this element, right? Is this part clear? That if k is equal to 0, you cannot even, like if your L is over here, then you cannot even take this element. So to take care of this empty window condition, what we will allow is head should be greater than equal to tail minus 1. So if tail is over here and my head is over here, okay, that means I have eaten nothing. Like it's like an empty window right now. Okay, and if it is forward, like if it is from like this particular tail to this particular element as head, that means inclusive of these two elements, it's the current like window that I'm maintaining in my 2 pointers. Okay, is whatever that we have discussed till now clear to everyone? Next we'll move to implementing this, of course, and it will make things more clear, but is what we discussed till now clear? Can I have a +1 on this and we can move to the implementation then? Okay, fine. So even if it's not clear, it will be very clear once we look into the implementation. So implementing 2 pointers is also very easy. So like in binary search, I gave you like a one quick style, right? That low, high, and answer. And with that, like low less than equal to high, just do this, like use this same part, change this few things, and it will work, right? Similarly, we will design a strategy for 2 pointers, and like that will work for every problem. Okay, like a simple syntax that will work for every problem using this head and tail that we talked about. Okay. So we don't need prefix sum in 2 pointer because we never talked about that in this approach. So let's remove this prefix sums from over here. No need of those things. Okay. So we will maintain an answer variable. Then we maintain a head, which is equal to initially. Let's fill that later. Okay. So initially, let's keep head as -1 and tail as 0. So tail starts at 0 and head is at -1, and it will try to eat next elements. Okay. The significance of -1 will come up once I complete the next part. So like, please bear with me for a few more lines and then I think it will make sense. Okay. So now while tail is less than n, so we will try. So tail is basically the L that we talked about for every window, right? So we will try all different L's from 0 to n-1. So that means like all different sub-arrays that are possible, right? And for each of them, we will try to push the head rightmost possible place so that the condition is not violated, right? Also, what we will do is we will keep something like count 0. Okay, that how many zeros are there in my like current tail to head window. Okay. Now while head plus 1, so while head plus 1 is less than n, so my head is at -1, right? So I will try to eat the next element that is available. So that's head plus 1, and if that is less than n, then there is a next element to eat for the snake. Okay, so that's what I will check. And can I eat that element or not? That we need to first of all decide. So if k minus, so count 0 plus 1 minus ARR of head plus 1. So what is this particular thing? 1 minus ARR of head plus 1. So if the next element is 0, this will be 1, or else this will be 0, right? If the next element is 1, then this will be 0, or else this will be 1. So that will be the new value of my count 0 if I increment my head pointer to the next element, if I take the next element into my window. And if this is less than equal to k, then I can take the next element, right? So this will be equal to, then we can take the next element. So we move our head one element ahead, and we will increase our count 0. by this particular value. And now note that when you're shifting things from here to there, like make sure you write the indexing correct because we have changed the head, right? Now, after this, so what is this doing? So for this particular tail, this while loop will try to push the head as right as possible, okay? And there are only two conditions, only two ways this while loop can break. Either there is no more element for the right pointer to move ahead, or you cannot take the next element into the window. Makes sense, right? So that means we have reached our rightmost point for this particular tail. Okay. So we just take the maximum for this particular tail and we move our tail ahead. So we will take a maximum. If head, now we will move our tail like one step ahead. So for this, I generally prefer to write two conditions over here. Head is greater than equal to tail. So there are two cases, right? Either head is greater than equal to tail. That means my window has some element. Okay. If my head is greater than equal to tail, remember we discussed this. If my head is greater than equal to tail, that means I have some element in the window. But if my head is before tail, that means I cannot even take one element in my window, right? So if this is the case, then what we are doing is we will remove the last element. So count of 0 minus equal to the whatever the last element's contribution was. So if last element was 0, then it will increase. So if this was 0, then this will be 1, and count of 0 in my window will decrease by 1. Okay, that I think this makes sense to everyone. Or else and then after doing this, I will increase my tail. Okay, or else if my window is empty, then I just make my tail plus plus because there is no element to remove contribution from, and I will make my head equal to tail minus 1. Because if I hit this tail else, sorry, I meant to say, if I hit this else, that means my head was before tail. So for the next tail as well, my head should be before tail. So I'm just resetting it to tail minus 1 so that it's like an empty window at tail. And then on this next loop, it will try to push the head as far as possible for this new tail. Okay. And this will work for all the windows and it will give me the answer in this max. So let me quickly do a quick brief over, because this is the first code that I've written on two pointers. This is understand to know the syntax, but once you follow this particular construct on every problem, it will be very easy to solve any two pointer problem. Okay. So we maintain two variables, head and tail. When head is less than tail, that means the window is empty. Okay, the snake is empty. Okay. Now first we try to push the right boundary as far as possible. Okay, so somewhere it's L, somewhere it's R. Okay, then we try to push the R boundary as far as possible. So there are two conditions: either there is a next element, or we can take the next element or not. Okay, so if both of them are true, like we can take the next element and there is a next element to take, we take that into our set, into our window, and we increment our R. So R becomes this new element. Okay. When we cannot take any more, that means for this particular L or tail, I meant to say, this is the farthest R that you can go into, right? So that's the max part that we are doing. And then what we are doing is, for this, since this is non-empty, what we will do is we will remove the contribution of this element from the count. We are maintaining this count of 0 in the window. So we will remove that contribution and increase our tail to the next point. So this will come to this, right? Or this part is only for this particular condition. Like let's say why I've written this particular part in this code. Let me explain that as well. This small part over here. Let's say this was something like this, that you had 1 0 1 and k is equal to 0, the condition we discussed. So when the tail was over here, my head was over here, right? Because I could not even take the next element. Okay, so next I move my tail one place ahead, so my tail will become over here. So in that case, my head should also move to this particular position, right? That's what I'm doing over here. Okay, and since the window is empty, I don't need to do any like count changes into the array. Is it clear? Now, any doubts on this particular code or any approach that we talked about till now? Feel free to ask. So this is all that you have in two pointers. Like this is the whole idea of two pointers. So if you follow this construct, I think you should be able to solve any two pointers code. Why head plus plus will fail in empty case? why head plus plus on which line, Shashi? Uh that it's perfectly fine. You can even write head plus plus. That's like, so this particular line means like we want an empty window, right? That's it. So even if you do head pluses, it will work. Like that's the same thing, right? If you always maintain the invariant that if head is less than tail, then it's always tail minus one. So if you make tail plus plus, then you can also make head plus plus. This is also correct. No worries. This is also correct. But generally, like this is like head equal to tail minus one means an empty window from starting at tail. That's what I think about when I'm thinking of a problem. So when you're practicing about some particular technique or some particular topic, also think about how you should be like implementing a particular problem and build a construct in your mind, so that when you're thinking about it in a new problem, you don't have to think about the construct on how will you implement it, right? Once I think about a two pointers problem that this approach will work, I always code it in this particular style and it works every time. So once you learn these correct like implementation styles, try to like use them repeatedly so that it becomes a habit whenever you need to code that same idea again, right? Even in a new problem. And for now, since you have not like if you have not built a new like previous practice on your own, you can like take, so that's what we are discussing over here, right? This implementation style, you can pick this up and practice the problems on this own with this style, and as you like learn with me this style, you will get a hold on it, right? Is this part clear to everyone? Can I have a plus one on this chat if everyone is clear with this? So in short, this is all that you need to know about two pointers. Of course, then the difficulty of problem can increase. Like, what do you need to maintain? Over here, we needed to maintain simple account zero, right? So what do you need to maintain? How do you apply two pointers on a problem? That's the different thing. That's where like problem solving comes in. But that's the all about two pointers. Like there is no more concept than this. Okay. So next we will take up another problem. So this problem, this particular consecutive window one problem, this we solved with three approach. One, binary search on the answer. Two, binary search on every L with prefix sum maintained. Three, or two pointers. Now, can anyone give me the time complexity of the three approaches that we talked about just now, like that I talked about? One is binary search on answer. Two, binary search on every L. Three, two pointers. Okay, so I will acronym binary search with BS and two pointer with TP. Okay, so just so that I don't need to write every time two pointer. Okay. And log in and log in and anyone else having any other idea? Anything else apart from this? Well, that's correct because that's the correct complexities. Binary search on answer takes order login. So this and login this we discussed in the last session. For every L, there are order n number of indexes, and for every index, it takes login to binary search because we have the prefix sum built in. And then for two pointers, we know it works in order n because we don't maintain anything. Like there are just two pointers moving forward. That's it. Okay. Is everyone clear up to this? Can we move to the next problem then? Okay. Let's then talk about this new problem. So let's suppose you are given n as the size of the array, and again a k. You're given the elements of the array a1, a2, a3, a4, so on up to an. And now you need to find the longest subarray of this array, which contains at most k distinct element. Find out the longest subarray with at most k distinct element. Okay. So how can we solve this particular problem? Any ideas? Even binary search will be okay. If you suggest binary search, that's also fine. Maintain a map. Okay. Can we solve this using binary search? So think about this particular problem and tell me, can you solve this particular problem using binary search? So no reply. If you cannot think of an approach, then like write a -1. That's also possible. If you think it's not possible, or like it should be, we can maintain a prefix sum of distinct element. Okay, so she says we can maintain a prefix sum of distinct element. Okay. Number of distinct, yeah. Okay, number of distinct element. Okay, I get your idea. But apparently this will not work. Make element as 1 for first occurrence. No, it doesn't really work like that, but make every element as 1 for. Yeah, there are some difficult ways in which you can do this, but okay. Okay. So what if the second time will actually create the like longest subarray? In that case, that will be wrong, right? Like you're saying that second time when it occurs second time, right? So second time might create the longer one. We are not that will not work. The one that Saji suggested, that is also wrong. Let me give you an anti-test case for that. So what happens is like the prefix. So prefix for sum, if you want to. So what do we need? So in that particular part, when we were searching for from a L, we wanted the sum of the range L to R, the number of zeros in the range L to R, right? Number of zeros in the range L to R. That's what we were searching for, right? And we use prefix sum. Now we need number of distinct elements in range L to R. Right? Now it turns out finding number of distinct numbers from L to R is not as trivial as it seems. Like it's to be honest, it's not even possible at the range of like AZ202, even after the course. Okay. It is possible, but with a very complex data structure. So we cannot find, like we cannot query the number of distinct elements in L to R. I'm not saying it's not possible, I'm saying it's not in the reach, okay, right now. It uses some sort of persistent segment tree to find out in order log n, but it is not of like currently of concern. So this is infeasible, right? So that's why we cannot use binary search for this particular problem. Why is prefix sum not working in this particular case? Because how do you like, what is the number of distinct element in this particular range? So you will say that, okay, the prefix distinct number of elements will be 1, 1, 1, 1, 1 everywhere, right? Then how do you find the number of distinct elements in this range if everything is 1, 1, right? So with prefix distinct, you can only maintain this much information, right? So how do you find out in a range if there is any distinct element? Makes sense, right? So like you cannot remove the contribution that easily from prefix sum. For sums, it's easy to subtract, but for distinct, you cannot subtract, because who knows when you're subtracting, was that the last occurrence or not? Okay, whether there is one element over here or not, right? That's the point. So prefix sum and number of distinct, like the approach that even Abhijit suggested, did not work in this one. And in fact, it's not possible to solve this in very easily. So rather, for this particular problem, binary search is rather like difficult. So we will move to 2 pointers, which is much more easier. And as Shashi and Parth suggested that, okay, we can solve this particular problem by using a map with the for the window. Okay, so what we are doing is, when we are from this particular L to particular R, okay, let's suppose for this particular L, this is the farthest that you can go, right? So that means the number of distinct is less than equal to k for this window. Now, if for this particular window the number of distinct is less than equal to k, then if I talk about this one more, like remove one element from this, from L dash, this will still be less than equal to k, right? Is this clear to everyone? That if from L to R, this satisfies the condition that number of distinct is less than equal to k, then even from L plus 1, or that is L dash after L, this is also true that from L dash to R, this will be less than equal to k. Clear to everyone? Can I have a plus 1 on this? So that means for L dash, R dash will be greater than equal to R. That means the condition that we talked about, this holds true in this particular problem. That means we can apply 2 pointers for this problem. Okay, so make sure you check this, like you will by automatically get a sense that, okay, can 2 pointers be applied to this problem or not, but it's a like good practice to like keep a quick check in mind that, okay, is 2 pointer even working? Okay, so basically if you remove an element, it should still work, like that's the whole thing. Okay. So 2 pointer can work, and what we need is, for this particular window, we need to maintain some structure so that when we try to eat the next element, like my head is up to this, and I try to eat the next element that is over here, if can I take it or not will depend whether I already have k number of distinct element over here or not, or if I have seen this element in the set already or not, right? Anurag, over there, this one, this particular condition, which part is not clear? So what I'm saying is, from L to R, if the number of distinct is less than equal to k, then from L plus 1 to R, the number of distinct is also less than equal to k, right? For 2, 3, 4, if this is less than equal to 3, then this is also less than equal to 3, right? Number of distinct element. Like smaller range is always favorable to keep it less than equal to k, right? So this property holds that we talked about in 2 pointers, and that's why. Is it clear now, Anurag? Yep. So we need some sort of structure to maintain this property of count of number of distinct, and I think we discussed about this in a session, that how do we keep count of number of distinct elements in a like in a structure, like insert element, delete element, and find out the number of distinct element in it, right? So that for that we use map, right? So now this is the place where it all comes like helpful, that now you can use that same particular like created custom structure or just a map where you like erase the element as well to quickly find out the number of distinct element. Okay, so let's move to the coding part then. Like, is everyone clear with the logic what we are doing? So from map we know that we can remove the last tail element very easily, and we can insert a new element as well. So that's what we need, and insert and delete and distinct was something we already discussed in STL sessions, right? So we will like use a map to do this particular operation. So is everyone clear with the logic? Can we move to the coding part? Can I have a +1 on the chat? So we need an array and things will remain the same. So I will just erase this part. I'll rewrite this. So it will be quite similar, but still. Okay. Now we always need these two things. So before we move into this, let's discuss one more thing. I think we discussed this. So how do we maintain the number of distinct in an array with inserts and delete in order 1? Did we discuss this in a session? This is also an important technique. So let's discuss that. So let's suppose there is this array. So let's talk about the constraints. So the array contains AI, and each AI is less than or equal to 10 to the power 6 and up to 10 to the power and 1, and this is the scenario. So this is the 2 pointers that we are talking about, the window. So with this particular constraints, can we maintain the number of distinct better than order login? Because if you use maps, it will take login, right, for maintaining the distinct. So we want to do it better than order login with inserts and deletes. With inserts and remove, we want to do it better than order login. So I think we discussed this once, how to maintain the number of distinct elements in order 1. Anyone having any idea? Priority queue? No. Yeah, maintain an array of frequency. True. So that's where this particular part comes in, right? 10 to the power 6. Why is this over here? So we can create an array of 10 to the power 6 and use that array as a frequency map. So whenever a particular element, like let's suppose x had a frequency of 0, and if we inserted and it became 1, as soon as after increasing it becomes 1, we know that a new distinct element has been introduced. And as soon as we decrease from 1 to 0, we know that a distinct element has reduced, right? So we can maintain a count of distinct elements using this particular logic. So we will implement this one in the code, because let's try to keep it as optimal as possible. Okay. So we will let's look at use something like this. Count of distinct equal to 0. Okay. And integer frequency array. So even if it's not clear, it will become clear right now. So when we have to insert a particular x, we increase its frequency, and if after increase the frequency of x got to 1, that means that element is a new element introduced, right? So we will increase our count distinct plus, right? Similarly, void remove frequency of x minus minus. If frequency of x after removal became equal to 0, that means there was this element was present in the set, but now its frequency became 0. So it's this operation that made it remove completely from the set. So a distinct element got removed. So count of distinct will decrease, right? So with these two operations, you can maintain like the number of distinct element in order 1. Is this part clear to everyone? Can I have a +1 on the chat? So I repeatedly ask you to like write +1. That's just because it's not clear on like everything is clear to you or not. So if you write a +1, that would be really helpful. So don't think like, okay, I'm saying repeatedly why to write a +1. Okay. And if you have any doubt, feel free to write that in the chat. Okay. Even if it takes time, if you like, even if I move ahead, write that on the chat. I will make sure that I come back to that. Okay. Next we have array of n, the array size. Okay, let's keep this answer. We want to find the longest window. Now tail is less than n. Okay, so now we will write this part. Okay, so initially everything is set to 0. It's ready. So now we will have while. So we will write the same thing. While head +1 is less than n. That means there is a new next element to take. Okay, and count of distinct is less than k, and frequency of. I'm first writing this and then I will explain this what I'm writing over here. Okay. So what is this part? So we are writing conditions for, first of all, there should be a next element, and if my current count of distinct is less than k, and if I take a new distinct element, so whatever element I'm going to take next, it has frequency 0. That means when I will take it, it will increase to 1. That means this new element that I'm going to take is a new element, right? That has not in my current set. So after like including this, my count of distinct will increase by 1. So my count of distinct should be less than k, not less than equal to k, right? If it is equal to k, then it will become k plus 1, and then it will be like troublesome. So it will not work, like it will violate the condition. So if we can take the next element, if the next element is distinct, we can only take it if my current count of distinct is less than k, right? Or my current count of distinct is less than equal to k, and the next element that I'm going to take is greater than 0, right? So it's like the next element that I'm going to take is something that I've already taken in my window. So next time when it is taken, like it's not going to like add a new distinct. So it's okay if my count of distinct currently is less than equal to k, right? So I can take that element. Is this clear to everyone? Like the check condition on how are we moving our head, like on two conditions: if there is a next element, or and the next element is like edible by this thing. Why am I saying edible? That means like after taking it, my like condition of number of distinct less than equal to k does not violate, right? Is the second condition needed? Yes. If what if frequency of error head is like greater than 0? So in that case, like we will have to check once, right? Like, okay, so you are saying that it will by default take it, right? So it will only take. So if I don't write this particular part, so you I can remove this particular part. I can remove this particular part. No, this will not work. This has to be there, right? Why are you thinking? Yeah. So what if it's greater than 0? Then this has to be less than equal to k. So which condition should I remove? I'm not sure. Like it's better to write this condition to be safe. Like I'm not sure which condition you're talking about. Like just one or this whole. I think without this whole it will not work because it is three ands in consecution. So all of these three will have to work. But I think this is the complete condition, right? So if either of them is true, then we increase our head and we then insert the element at head, right? Insert ARR of head. Makes sense? That we created over here. Insert function. Okay. Then we need to find out the like longest subarray. So we take the max. Right? And then the same part of the previous code. If head is less than tail, then tail plus plus and head equal to tail minus 1, or else you remove the element at ARR of tail and you make tail plus plus, right? And then after that answer is printed, right? Is this part clear to everyone? Second condition, second part. Okay. So you're saying this part, right? Okay. So this just says when is this going to be true? ARR of head plus 1, the element that is next, its frequency is greater than 0. That means that I have the window that I'm currently maintaining from L to R. Let me write this. I think that will make sense. So I have a window from L to R, right? So I have some, let's say I have seen 2 in between this L to R and the next element is 2. So in that case, the frequency of 2 is equal to 2 already. And then I'm going to take a new element. So if this is a new element, okay, if this is not a new element, I mean, sorry, this is not a new element, 2 is not a new element. So in that case, you can just simply take this part, like this part. Okay, this part is a bit redundant, we can remove this if you want to, but okay, so we can take a non-new element only when count of distinct is less than equal to k, right? And like this is the part which checks that is it a non-new element, like it's already present in our like set that we are maintaining of this window. Okay, if it's already present, then the number of distinct element will not increase. So that's why we will increase our right pointer by 1 and it still works, like it's still at most k distinct. Okay. Is this clear now? Okay. So now let's quickly talk about one small change in the problem, like quick variation. Let's say we have to find the longest, right? So let's say I change this to count the number of subarrays with at most k distinct elements. So now you all need to tell me what are the things that we need to change in the code. I hope you got the question right. Like now you need to count the number of subarrays with at most k distinct elements. So I can say that this same code will work for that as well. Just we need to change some counting logic, right? So what are all the things that we need to change that will work for like any particular input in this scenario? Any ideas? Done, right? That's all. Now why is this working? Let me explain you that. So two pointer also helps us to count this idea for every L. So in binary search, we generally can count, we can generally find out the min and max, right? So this idea for every L, find out the largest R also helps us to count. Why? Because let's take this particular, let's move to a fresh new page. So let's suppose this is the window and this is your current L, and you find out that let's suppose this is 1, 2, and up to 3 element you can take, this is your R, right? So now with this particular setting, how many distinct subarrays are there which start at this particular L and has at most k number of distinct elements? So we know that this was the R point, right? So if I go up to this particular part in the subarray, this is greater than k number of distinct element, right? This we know. So from L to R, we know that okay, this much contains k number of distinct element. So at this particular window, we will count the number of subarrays that end at L, like that start at L and has k less than equal to k number of distinct elements. So that will be 1, 2, 3, 4, right? And that is nothing but R minus L plus 1. Is this part clear to everyone? Okay. So this is where like two pointers, and even when binary search with particular L comes into play, then when you have to count the number of subarrays, okay. So is this whole problem clear now? Like then this is the one variation that I thought about talking for this particular problem. So any doubts on this particular problem of finding the number of distinct less than equal to k? Any doubts on this one? So can I have a yes from everyone if like we can move to the next problem then? That's new one. Okay. Okay. So now we will talk about one different style of two pointer problems that is like not similar to this particular construct over here that we talked about, but it's still prevalent at times. Okay. So let's first talk about the problem. So I think a lot of you might, if you have done some preparation for interviews and other things, you might know this particular problem. So you're given a particular array, okay, and there are some, you need to choose, let's talk about, you need to choose 3 indexes such that ARR of I, j plus ARR of k is, let's say, less than, is closest to target, closest to a given value x. Okay, so you have to choose 3 elements out of this array. No two should be same, okay, such that the sum of the 3 elements that you choose should be closest to the given, to a given value x. Okay, okay. So in the problem you are given as input n, okay, and the array is given to you, and a value x is given to you, such that you want to make the 3 element that you are choosing sum closest to x. Okay, and the size of the array is up to 10 to the power, let's say up to 5,000. So you need to find you have to find any one such pair, something like that. Okay. Is the question clear to everyone? Choose three element. None of the three should be same. Like it should be pairwise distinct. Distinct. Yeah, it should be pairwise. Like the indexes should be distinct. I mean to say, I is not equal to j, is not equal to k, is not equal to I. Okay. Okay. And this sum for these three elements is should be close to this particular sum, this particular given x. Okay. Closest to that, as much close as you can make it. So how many of you know this particular problem already? Okay. Okay. So now let's then discuss the idea for this particular problem. I think the ideas, there are lots of different ideas for this, but the main thing is you need to like, so there can be different ideas, but you should be able to do this particular problem considering this particular condition as well, right? For those who already know this problem, they can think about this particular problem that let's suppose you have to choose four such elements such that sum is closest to x. Okay. And sum the sum is, let's say, closest to x and the constraint is same. So if you already know this problem, so anyways I will be discussing this. So I think if you know the two-pointer approach, then it will be repetition, but still, so you can think about how do you solve this for four different elements such that sum is closest to x. Okay. And constraint would be, let's say, 2000 or 1000 or something like that, a little bit less, but that's fine. So now let's talk about this three element problem. Okay. So first of all, there is an obvious order n cube solution that like you choose three elements out of the array and like make three loops and choose three elements, take the sum and find the abs of difference and take the minimum, right? That's one way. Okay. But that's order n cube and that will not pass for this particular problem. So we have to solve this particular problem in better than order n cube, right? So since we have to choose three elements, the order of the elements does not matter, right? So it sometimes helps in such problem to sort the array. Okay. So we first of all sort the array, and from now on I'm assuming that the input is sorted as well. Like I'm assuming that input is given as sorted, or if it is not given, we will sort it. Okay. So let's suppose we are now given a sorted array and we have to choose three indexes and we have to find this. Okay. If it's not sorted, then we can obviously sort. Like sort can be very easily done in this particular constraint, right? Now, with this in place, let's talk about how we can solve this. So what we will do is, there are three pointers, right? There is a I, let's call this I, let's call this J, okay, and let's call this window K, okay, some three elements. So what we will do is, we will iterate on the element J, let's say, okay, and we will use two pointers on elements I and K. So what are we saying when you say two pointers? Okay, so let's say we have an array. Okay, so let's suppose we fix our J that this will be my second highest element. Like there will be three elements, right? I greater than J greater than K. So let's say this is my element that I have chosen. Okay, this is one of the three elements, and in fact the middle one, not any one, just the middle one. Okay, so now there will be one element in this part and one element on this part, right? So what we will do is, we will start with this first element as I and this last element as J. Okay, sorry, the K. This is J. Okay, the first element as I and the last element as K. Now let's talk about the given target X. Now there can be few cases that happens at this particular scenario. Let's talk about the value of ARR of I plus ARR of J plus ARR of K. Okay, let's talk about this. And the value of X, okay, and move. Okay. So let's suppose this particular sum that we are talking about, this is the sum. We want to make this sum closest to this element X, right? So let's suppose this element, this sum is less than X. Okay. Let's suppose this sum is less than X. So what we will do over here is we will try to either increase I or decrease J, decrease K, do either of them, like any one of them. But which one will give us more optimal value? So it was already less than X, right? So if we decrease K, note that this array is sorted. So if we decrease K, the value of this sum is going to decrease, right? And anyways, this sum was already less than X. So if we decrease K, this sum is going to drop much further and this gap is going to get higher, right? Yeah. So if this sum is less, then we should do I plus plus, so that this first, like, so that this sum gets a higher possible value, right? So we will consider this sum, we will take its max with like this minus X abs of that. We will take a max, like we want to minimize it, so we will take a min, and then we will increase I, because increasing I will increase this sum and we have a better chance to meet at X, right? But let's suppose you increased your I up to this particular point and then your sum went more than X. Like it might be that, okay, this element was 2 and this element was 4, and let's suppose like this plus this was equal to, let's say, 16 and your X was 17, right? So this was less than 17. So you can make a difference of 1 and then you try to move I, okay? So but as soon as you moved I, this sum went from 16 to 18. So now you have overshoot your target, right? So like you have gone beyond that. So it is now greater than it. So in case this sum is greater than X, what do we do in that case? Which pointer do we move? Anyone? K, right? Yeah. Because my sum is more than X and I want to make it closer to X. So what I will do is I will decrease my sum. So increasing I will decrease sum, or decreasing K will decrease sum? Decreasing K, right? Because this is sorted array. So if K moves backward, it's like a lower element that it will take, right? And if it is equal to, then which one do we move? Yeah, to be precise, either. In fact, you don't need to move. You have got three, yeah, you have got three elements that is equal to X. So that's your answer. Break out there and there. Like that's your answer. Done. Okay. So print it and exit. That's it. You can do that, but ideally you should like print, save it and return. Okay. Because you cannot do better than that, right? What's there to search anymore? Makes sense, right? So like answer and return. Answer and return. Okay. Is this idea clear to everyone? So this is one of famous interview problems. However, like this is one style of two pointers that is also that also exists, that you have like one pointer from the start of the array and one pointer from the end of the array, and you move one front, like either the first one forward or the last one backward based on condition. Okay, this is another style of two pointers that exists. However, this is not very common in competitive programming, because there are other ways to solve such kind of problems in order login, kind of like with an extra login you can use a multiset and solve this problem if you want to. However, since that's why I deliberately made the constraint 10 to 5,000, so that login does not work. For 5,000 you will have to use n square login will kill. So let's quickly look into code of this. Don't think there is much to code. I will quickly code this problem. I think I should not take much for this particular problem. Nk array will be the same. We will change this particular pointer things. So we will have to sort the array, of course, because okay, and then we will create like a what is the closest that you can get to an answer. Let's say that answer is equal to 3e18, right? A very large value. Now for integer I equal to 0, I equal to 1. So let's move loop onto the middle element. Let's call the middle element I. Let's loop from I equal to 1. I is less than n minus 1. So I can only go from 1 to n minus 1, 1 to n minus 2, right? Because there has to be some valid I and k. So a quick optimization over there. But, okay. So integer low is equal to, the low will be like, so let's use the naming same as what we discussed. That should not. So integer I is equal to 0 and integer k is equal to n minus 1, right? So first and last element is where we start from. Now while I is, this would be k, while I is less than j and k is greater than j, what we do is answer equal to minimum of answer comma abs of ARR of I plus ARR of j plus ARR of k, right? Minus target. So target is k. Sorry, this should be target, right? This should be x. Yep. Right. So this is the, and then we write the two conditions that if ARR of, like if this is less than x, then we move I plus plus, or else j minus minus, right? So anyways, we need to print the answer. So if it becomes equals, we can break off if you want to. Like you can write one more else condition. If it's equal, break. That's also possible. And then you can print the answer. But okay. So this will work with integer. So we have these things in integer. Let's make it long so that you don't get an error over there. Yep, that's correct. K minus minus, right? Yeah. Is this part clear? Like we are sorting the array and just moving the 2 pointers as we discussed. Quick code, but a neat idea, right? So we can solve this particular problem in n square rather than going into n cube on choosing all three elements, right? So we are like optimizing on one particular element. Even if we had to choose two elements to get one sum closest to a target, you could like, we just looped on the middle element, right? So if there would have been just two elements, we could have just taken 2 pointers, one from start and one from end in the sorted array, and then would have like moved based on this particular condition without this ARR of j. That's all. That's all the change that you need to do. For 4 elements, that's the assignment. Think about it. N cube, yeah, no, we are looking something better than n cube. So yeah, for 4 element, we can do, yeah, for Amisha is saying, what Amisha is saying is right. That also is possible for this particular problem to solve it in n square log n. That if you have I, j, and k, so what you can do is you can like loop on I and j, and for the k you maintain a like a multi-set, and then on or maintain a set, and on set you can like find out using lower bound and upper bound, like find out using lower bound and the element before that to get the sums. That will work in n square log n, right? So for 4 elements, you can obviously do it in n cube because that would be similar to this particular problem. But let's think about how you can do that in better than order n cube. It's possible to solve it in less than order n. But that idea is not very easy. We will take this problem up in some later session. Okay, but it's solvable. That's what I say. You can solve 4 elements with 2 pointers in n cube, because that would be just like a one and another loop in between in the middle element, and the last 2 elements will 2 pointer. So that is there possible, but you can do better than that. Okay. Now let's talk about another problem on two pointer then. Is this particular problem of three elements clear for everyone? Okay. Is this part clear? Can I have a plus on the chat? Okay. If this one is clear, then we will pick up one. Stop. Let's talk about this particular. Now let's see one problem which is like a current contest standard questions of 2 pointer. Okay. Like these can be a good contest standard question of 2 pointer. So whatever we discussed till now was like still educational questions for 2 pointers. What is the current scenario of contest competition questions on 2 pointers? Let's look into one of those. Okay. So let's say you are given an array n and you are given a number k and a number d. Okay, there are three numbers given to you, and you're obviously given the array. So you need to find a subarray in this array, a subarray in this array, such that it follows some conditions. Okay. The conditions are: number one, the number of odd numbers in the range should be less than equal to k. Okay, like whichever subarray you are talking about, the number of odd numbers in that subarray should be less than equal to k. Okay. The second condition on that subarray should be the sum of subarray. The sum of subarray, by sum of subarray I mean to say the sum of elements of that subarray. Okay. Sum of subarray should be less than equal to d. Okay, this is the second condition. And now with these two conditions in place, you need to find one such subarray which has the maximum sum. Okay, find max sum subarray holding like maintaining like which holds two, which takes these two condition into hold, like that subarray should satisfy these two conditions, right? So find the array with maximum sum. So obviously that sum will be less, like the answer will obviously be less than equal to d, because the subarray that we're talking about satisfies this condition, but we want to make it as large as possible, so we want to push it towards d, but it should follow these two conditions. So with these two in place, find out the subarray with this. And the elements can be both positive and negative. It's not all positive. Okay, like it can be negative, positive, mixed. Okay, and for negative numbers, we define that. Okay, we compare the abs of that number as positive, like odd or not. I hope you all know that. Okay, -1 is also an odd number, right? Like you can remove negative sign and check for odd property of a number. Okay, that's defined in the problem. Let's say. So we need to find the subarray with these two property and the maximums. Just print the maximum sum that you can make. Think about this problem for a minute. So I will give you maybe 1 or 2 minutes to think about this problem, because this is a good problem and you should, like, ideally you should try to think and then solve the problem. So in our session, we generally try to like look into ideas directly. But when you're solving problem, you should ideally give a time to think about the problem on your own before looking into hints and other things. Like ideally, you should not even like look into hints. But okay, if you're like stuck for a long time, then that's it. Keep your practice as close to the contest setting as possible. In contest, you will not get either the test cases or the hints or anything. So out of the two conditions, prefix sum for odd values and find the odd values, prefix sum for odd values and find this subarray which satisfies the odd condition. So how do you satisfy both the conditions together? That's like, that is difficult of it. Like, so there are negative elements present, right? So yeah, sum is not monotonic, exactly. There is negative element present. So it's not binary searchable as you're thinking, I think. Like the sum less than equal to d part is not uh, binary searchable. The first part is okay, like you can do the binary search on odd number because that's monotonic. That we have already discussed, but the second part is not. So out of the first and second, which one is easier to maintain in binary search or two pointers? Can I have the answer from everyone? Like, first, right? Like we have already seen a problem with the first one. I think like that directly suggests that the first one is easier to maintain two pointers, but the second one is really difficult, right? Like how do you maintain that? So we will maintain a two pointer on the first, and we will build a structure on the second, something like that. So let's like understand how we will be doing this particular problem. So we will do the same thing that we talked about, that for like if this is the array, if this is your L, we will find out the farthest R, okay? And then from this L, we will try to consider all the subarrays which out of all the subarrays which has sum less than equal to D, which subarray has the maximum sum, okay? So we will try to find this out. So is this part clear what we are trying? That we will try to find out this particular window first of all, okay? This particular window where this L and R satisfies the first condition, that okay, from this window to this particular part, like the number of odd numbers for this L is less than equal to K, right? For all of these elements. And then after that, it will become more than K. Then from this L, we will consider all windows, like there would be order R minus L plus one number of windows in this, okay? Out of all these windows, find out the window which satisfies this and hands the maximum sum. We will try to find this two together in this particular window, okay? So I hope you are getting an idea on how to maintain this first part very easily, right? I think most of you can now do this first part. How many of you are confident that you can maintain the first part, like the L and R for the first part? Right? The first part should be now clear. But this second part is really the troublesome part because it's not monotonic. So what we will do is, there is this subarray sums, right? There are this subarray sums. Now subarray sums are really difficult because in two pointers, when you remove the element, what you will have to do is remove sum from every element, right? Like you will have to remove a particular element's contribution to all the subarray sums. So what we will do is, we will maintain a multiset of the subarray sums. What we're trying to do is, we will maintain a multiset of all subarray sums, and when we like remove the L, we will like remove this particular element from all the elements in this subset in the multiset. And when we add a new element, we add that element, we add one more window from that element to this L as into the multiset. That we can do, but this is very heavy on operation, right? So to maintain this multiset, what we will do is, we will maintain these ranges in terms of prefix sums, okay? So let's call this, so let's now like move a bit down and start with a new array. So if this is the L and this is some particular J less than equal to R, okay, some J less than equal to R. So we now know what is my R, okay? So if I want to consider the prefix sum from, like I want to get the sum from L to J, so that would be nothing but prefix of J minus prefix of L minus 1 is equal, this is the value, right? And this has to be less than equal to D, right? So this is nothing but prefix of J should be less than equal to prefix of L minus 1 plus D, right? This part is clear to everyone that for any J in this particular window, if the sum of that subarray should be less than equal to D, then this is the condition that we are talking about. Now, this part is fixed when we are iterating on L. So L is fixed, right? So this part is fixed. So out of all possible J's in the range L to R, we just need to find the J which has prefix of J as the maximum value. Okay. So we have to just find the prefix of J that has the maximum value satisfying this particular condition. So now, in this particular part, how do we then find out the prefix of J that is just less than equal to this, because this has to hold, and then the sum will be maximum only when prefix J is maximum, right? So what we will do is, for all the elements in this range L to R, we will maintain their prefix sums, like prefix of J. So this J lies in the range L to R, right? So we will maintain this prefix of J value in a multiset, so that we can find out the largest value of prefix of J less than equal to this particular value, which we can do in a multiset. Okay. Is this idea clear? That what we're doing is, we are maintaining a 2 pointer on the first property, which maintains the count of, like, which gets us the largest range for a particular L, that maintains the first property, and for all that elements in that range, for every endpoint possible, we are maintaining the prefix sum, this prefix of J, all the endpoints that are possible for that range from L. For all that endpoint, we are maintaining the prefix of J in a multiset, and we just need to find out of all those elements which satisfies this condition in the multiset, what is the largest value of prefix of J. And that in a multiset can be done using an upper bound operation, right? Do an upper bound, come back one element, and that's the element that is just less than equal to some particular fixed value. Now, as we know that L is fixed, this is a fixed value in total, so we can find this prefix of J if we want to. Is this idea somewhat making sense? We will code this and then it will be more clear, but is it somewhat making sense? Anyone else? I think only one. Which part is unclear? Can I have a plus? Like, can I have a part where it's not clear? Multiset part. Okay, so what are we maintaining on the multiset? So what is 2 pointers? We basically do a movement of, like, we remove one element and insert a new element, right? So when we're maintaining the multiset on the first property, that for this particular L, what is the largest R, what we will do is, for all this element in the window, we are just putting the value of prefix of J for any index J that lies in between the range L to R. We will insert that prefix of J in the multiset, and when we like remove the last element, we remove this prefix of like L from the multiset, that we can maintain, right? So we are maintaining a prefix sum. We are maintaining a multiset of the prefix sums of the indexes in between the range L to R. So that is what this multiset contains. Multiset contains the values of prefix of J, which is like in the range L to R, okay, for all J in the range L to R. Now we know that any subarray that starts at L, a subarray that starts at L, so follows this condition, right? This is the prefix sum for any J. This is like, out of all J, this has to hold true for any J that is the ending point of that subarray, and L is the starting point. So this has to hold true as per the given condition. So out of all those prefix values in the multiset that satisfies this, we need to find the one prefix J which is highest, because as prefix J will be higher, this is the sum that we want to maximize. What do we need? We need the maximum sum subarray, right? This is the maximum, this is the sum. So to maximize it, this should be higher, right? This is fixed, so this should be higher. So we want to find this as high as possible, but still less than equal to this. So this type of query can be handled in multiset, because we can do an upper bound and then come back one element to find the element less than equal to some particular element in a multiset. Okay. So anyways, it will become more clear when we code, but Now is it clear? Can we move to the coding part of this? Can I have a +1 for that? Any doubts on the theory part of this? So let's try to code this particular one very clearly so that each and every part is clear. And as we now code things up, you might see that, okay, one code might need a lot of different things that we have discussed earlier. So it keeps giving you a practice of other things as well, right? We need multi-set and other things. So that's why a good command on STL is like a kind of a must, I must say, because without that, it will become difficult to use that frequently in other problems. So we will need long in this particular problem. Okay. So let's keep everything in the column only for this particular. So since we are using 2 pointer, we don't need anything in global. So we have NKD, K is the odds, D is the sum, right? So we will need to build the prefix sum as well. So let's build the prefix sum together. Right. So now we have a the 2 pointers part. So we need a head and tail, of course. So head will be equal to -1, tail will be equal to 0 initially. That's the standard thing. Now we need, yeah, sure. Now we need some things to maintain. Now we need a multi-set of prefix sums, right? So we need a multi-set of prefix sums. So since array can be go up to, let's say in the problem, array elements can go up to 10 to the power 9. Make sure when you are building prefix sum, you keep it in long because then or else it will go, right? Then we need something called odd count, right? Because how many elements of odd have we taken till now? And out of all the subarrays that we're talking about, what is the best sum that we could create till now? So let's take best as some negative infinity -1 E18. It should work in this particular problem. Okay. And then again, the same syntax that we have while tail is less than n. Okay. Now try to push head as far as possible. Head +1 is less than n. And two conditions: odd count is less than k, and ARR of head +1 mod 2. Okay. So if it's like non-zero, then it's false, then it's odd, or else odd count is less than equal to k and ARR of head +1 mod 2 is equal to 0, right? If it's even, then you can definitely take it. So if these are the two conditions, then what we do is we increase the head, right? If ARR of head is mod, if ARR of head mod 2, if it's an odd number, then odd count plus, then we insert the prefix sum of this particular index, prefix of head, sorry, empty dot, this should be insert prefix of head, right? So we will insert this particular prefix sum at the head, in the multi-set. Okay, makes sense. Now what we will do is we will keep, okay. So now we need to find the particular element which follows this property and is highest, right? So we need this particular element, prefix of L-1 plus D. So we will, let's save that in a variable temp. Let's say temp is equal to D plus prefix of L-1. So just to like safe check, if I is greater than 0, prefix of I-1, sorry, this should be tail -1 or else 0, right? This is the temp that we're talking about, right? Now how do we find the element that is just less than equal to D? We need to get the value, right? So we will use some iterators. So for that, what we use iterator empty dot upper bound this particular value temp. Okay, so we find the element that is strictly greater than temp. Okay, strictly greater than temp, and then we come back one element. But if my it is equal to begin, empty dot begin, so then there is no before element, right? If after this search my it points to the first element, then I cannot come back. So that means there is no element less than this available in the multi-set, so I cannot update anything. So I don't do any update in that case. So if it is not equal to empty dot begin, then only I can come back a step and like get an element that is less than equal to that value. Okay, so in that case I do an it minus minus. Okay, and then whatever that value is, I just update my best as best comma star of it minus whatever the temp value is. No, this should not be temp. This should be equal to this value. No, this is not exactly equal to empty. So what we are searching for over here is we want to find the element that is less than equal to prefix this particular value, right? So if we search this, if all elements are greater than this particular value, then it will point to the first element of the multi-set, right? So that is what we are checking. If all elements are greater than this, then there is no potential solution. So even though it's not empty, there is no potential solution. That's what we are checking. Okay. So this part is over here. Now, if head is less than tail, what we do is we have the standard style. We just do the same thing, tail plus plus and head equal to tail minus minus, because there is nothing to like, you don't need to maintain anything because the state is completely empty. It's already in reset mode. Okay. Or else what we do is if ARR of tail mod 2, like if it's an odd number, then odd count decrease, because you are removing an odd number, so it's odd count decrease. Then we have to erase the prefix sum of the last element, empty dot erase, empty dot find. So I hope you know that how to erase one occurrence of that prefix sum, because same prefix sum can happen multiple times, right? Value of the prefix sum. So we just want to remove one occurrence of that element. That's why we maintain multi-set rather than set. Okay. This is there. That's it, right? And then like if best is equal to minus 1e18, then there is like no solution, like it's impossible, right? Like there is no such subarray. Or else you print best, like whatever the best value that you created, right? Something like this. So is this part clear? This is the main part. Any doubts on this one? Is everyone clear with this? Can I have a plus one on the chat if everyone is clear? Okay. So this type of question can come up in any context, and like it will be fairly medium level question, not a easy, I would say. Okay. So I think these are the different styles of two pointers. So let's quickly go through on what we discussed today. So we talked about two pointers from the core, that okay, when we start with this binary search idea, for every L we find out R. So we observe that a property is like holding in place that okay, whenever we increase the particular L, the R also increases, right? This particular property over here. So if this holds, then only we can optimize it using two pointers. Like quickly coming back to this, what is the complexity of this particular code? Can someone give me the complexity of this? Just try now. Saurav says n log n. Anyone else? Okay. Yeah. It's in fact n log n. Yeah, it's n log n because the time complexity of 2 pointers would be, let me explain to you what the time complexity is. So how do you analyze the time complexity of your code of 2 pointers? So there are 3 parts to the code, right? While tail is less than n, okay, there is this part. Then there is this portion over here that we call push head, okay, as far as possible. Then we have something like an update answer, and then we have a portion which is like update tail, right? So this push head part happens at most order n times. This will happen only uh, order n times in total. This will happen only order n times in total, and this will happen order n times in total. So like order n times multiply with each of their complexities. So push head in this particular part is order log n. This is order log n. This is order log n. So it is in n log n in total, right? Okay. So coming back to this. So this idea of prefix sum, and so prefix sum is now like a very common tool that is used with any other technique. So that's why we generally discussed prefix sum earlier. It's like a tool that is used in every other topic. So, so with 2 pointers, we just have that property, and it helps us in problems like this where like it helps us in maintaining properties that is difficult to query from L to R in binary search. Apart from that, it also helps us in like maintaining this count of subarrays. So binary search does not help us with counts directly. Like if you binary search on the answer, like if you want to find count as the answer, binary search won't be helpful, right? So but still 2 pointers and binary search on every L can help you. Okay. So we talked about this particular idea. Now this idea was also important, that distinct element in smaller range, you can maintain a prefix, you can maintain a frequency array, and that would help you to solve better. Okay. Now we talked about this particular idea where we like move 2 pointers from first and end, and that we solve accordingly. So this is also like a very famous idea that is used in 2 pointer problems, particularly like famous in interviews at least. And then we talked about this particular problem where you have multiple constraints to be held. So one of the constraints like got maintained by 2 pointers, and out of all the every other possible subarrays, we only check those which are valid using a multiset, and multiset also gives us the maximum of that. Like that's a good feature of multiset, and hence we are able to solve this particular problem using 2 pointers, right? So in 2 pointers, you will have to think about whether 2 pointer is applicable or not, and then how do you can you maintain that? Can you maintain the property properly? That's all. That's the true thing that you should like think about when you're thinking, okay, can this problem be solved with 2 pointers or not, right? Is this part clear? So that's all for I think from today's session.